Oh, hi there. This is Stoichiometry, mass relationships. Wowee! Since moles can't be easily counted, it's more practical to measure in terms of mass. We saw this in Unit 2. Oh, remember this guy? 1 mole equals molar mass in grams. Eee! We're going to use that again. Oh yeah, it's coming back. You thought it was dead? Nope, just kidding. Here it is again. Let's do a little bit of warm-up. Make sure we use this formula correctly. I want to know how many moles would be in 3.45 grams of tricarbon hexahydride. So we're looking at a relationship between moles and grams. We have that relationship. I just recapped. 1 mole equals molar mass. We're going to set up our ratio. You can pause the video now if you like, and then continue after you've tried it yourself. If you're like, oh, I need more help than that, then just keep watching because I'm going to solve it for you anyways. So our setup is always the same. What am I looking for? Equals, what do I have? Then it's time to use my handy-dandy conversion factor. In this case, I want moles on the top, and I want molar mass down below. Now, I don't have a molar mass yet. I've got to figure that out, of course. So the first thing I need to do for molar mass is figure out what my formula looks like. I have a tricarbon, C3, hexahydride, H6. So I'm going to do my molar mass for 3 carbons plus 6 hydrogens. I'm getting the value of 42.08. You should get something similar. Grams will cancel. I'll do my math, bringing it to 3 significant digits, and I've got 0.0820 moles. I'm going to add that 0 on the end so that I maintain those 3 significant digits here. Remember this stuff? Oh, yeah. All right, let's try this one. If you watched me do the last one, try this one on your own first. What would be the mass of 0.56 moles of ammonium carbonate? Pause the video now. No cheating. If you're playing, it's because you just paused and completed this yourself. I'm going to solve for now. What am I looking for? Same setup as always. I'm looking for mass. What do I know? 0.56 moles of ammonium chloride. I'm setting up my conversion factor. It's the same one we just worked on since we're still looking at a relationship between moles and mass. So I want mass on top, so my molar mass will go here. And I want moles to disappear, so my moles will go down here so I can cancel them out. Therefore, I'm stuck at the same spot I was last time. I need to figure out what ammonium carbonate looks like using my periodic table. These are both on the back of the periodic table. They're both polyatomic ions. So if we go back there, ammonium is an NH4 with a 1+ charge. Carbonate is a CO3 with a 2- charge. So when I cross over, it's going to be 2 NH4 groups partnered with 1 CO3 group. My molar mass then should be 96.085 grams. And when I do my handy-dandy math here, I should be able to get 54 grams. And hopefully you got the same answer. So how do we put it all together? Darn it. Stupid arrow. Let me just draw that in. So when we are putting all this together, basically we're going to marry, I use the word marry. We're going to marry yesterday's ideas, that mole to mole ratio, with today's ideas, mole to mass conversions. Because usually in real life, I have the mass of something and I want to use it to find the mass of something else. But to tie 2 ingredients together, I need its molar relationship because the coefficients is how I tie one ingredient to another ingredient, and those are mole relationships. So here's generally what our path is going to look like as we get into day 2 of stoichiometry. Typically, I'm going to start with the mass of a reactant. Then I'm going to convert it into a mole. Follow the blue arrow. I'm going from mass to mole in stage 1. To go from mass to mole, I use my 1 mole equals molar mass conversion factor. And if I'm looking for moles, I would put my 1 mole over top of my molar mass. In step 2, once I have moles of any ingredient, I can do a mole ratio, which I learned how to do yesterday, to find moles of anything else. So stage 2 is to find moles of one thing and turn it into moles of another using the coefficients. So in this case, the flow chart is from reactants to products. I could just as easily go backwards. I could also do the same patterning with 2 reactants or 2 products. You'll see lots of variety. Once I convert moles of one thing into moles of another, in this case reactants to products, I can now turn those moles back into a mass because usually that's what I want to find. For instance, I might say, okay, I want to figure out how much product I could make if I had 10 grams of reactant. So that's where we would go with a question like this. We're going to turn this chemistry into something quantitative. So step 3, we would take those moles of product, we would use our conversion factor, 1 mole equals molar mass, we would convert back into mass. Because we're going from moles to mass, we would use the conversion factor with molar mass on top of moles. So this is just sort of our little cheat sheet or overview of how we put a bigger stoichiometric question together. 3 steps, 2 of them are pretty much the same, mole mass conversions, and then we have that mole ratio in the beginning, or in the center. The mole ratio is from yesterday. Woo! All right, stoichiometry can go in both directions. So I could give you a mass of reactants and ask you to find moles or mass of product. I could also go backwards and say, okay, here's the mass of the product. How much reactant would we need? I could also give you 2 reactants and say, okay, if I wanted, if I only had 15 grams of reactant A, how much of reactant B would I need to use? Or vice versa, I could say, okay, I want to make 17 grams of product A. How much product B would I inadvertently make at the same time? So any combination, any 2 ingredients on a balanced equation, I can do that same 3-step stoichiometric problem. Let's try it. I know you're excited. So here's our question. How many grams of NO would be made if we use 22 grams of O2? As per usual, anytime I'm doing stoichiometric, I need to start with my balanced equation. I've given you a balanced equation there. Just to follow the same steps as always, the first thing I'm going to do is I'm going to write down what I know, what I'm looking for. So I was given 22 grams of O2, and I want to know the mass that I can make of NO. So 3-step process. Step 1. I'm going to take my 22 grams and I'm going to convert to moles. I'm going to look for moles of O2 using my 22 grams of O2. My conversion factor is my 1 mole equals molar mass. Moles on top, molar mass down below. My molecule is an O2, not an O. Also, I just want to reinforce the fact that when I'm looking at molar mass, it's the molar mass or mass of 1 mole. So it's 1 O2, not 5. Even though there's a coefficient, that does not play a role in molar mass because molar mass is mass per mole. So do not include the 5 here. Just the molar mass is 2 O's. You'll use those coefficients in step 2. You don't use them until then. So that means 2 O's have a molar mass of 31.998. You could have just rounded that to 32 to be honest, but I'm going to be real particular. Sorry for the interruption there. All right, let's keep going. So our math will give us 0.688 moles. We now have moles of oxygen. Having moles of anything is golden because once you have moles of one thing, you can find the moles of anything else. And our goal, of course, is NO. So that's exactly what we do in step 2. In step 2, we're going to find the moles of NO using the moles of O2. This is exactly what we did yesterday. So don't panic. If you're like, I don't know what's happening, take a deep breath. This is exactly what we did yesterday, a mole ratio. So I'm using moles of one thing to find moles of another. This is where my coefficients come in. It's the only time they're going to come in. I'm looking for moles of NO, so I'll put moles of NO on the top. And I want to get rid of moles of O2, so moles of O2 will go on the bottom. Mathematically, zippity zip, what do we get? I want to say 0.550 moles. All right. Now that we found moles of NO, I can do that conversion factor, 1 mole equals molar mass, and I can convert back into mass, and that is step 3. Mass of NO using moles of NO. This is right back from unit 2, where I'm using my 1 mole equals molar mass, and we recapped that already today. So again, we've got our 30, NO is 30.006 molar mass over 1 mole. And my final answer then is 17 grams. Dun 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 dun! It's a bit of a work, but you know, got there in the end. That last one was so much fun. I say let's do it again. How many grams of NH3 would be needed to produce 85 grams of H2O? I've given you a balanced equation. Don't say I never gave you anything. Well, let's start the problem off as per usual. We're going to pull out, what am I looking for? What do I need? So I've got a mass of NH3 that I'm trying to figure out, and I was given 85 grams of water. That means that I'm going to start my problem with water. So I'm just going to start my problem physically under the water as well, just to keep track. And my first move is to take those grams of water and to turn it into moles. Again, the whole point of turning it into moles is because I need to relate one ingredient to another, and I can only do that through coefficients, which is a molar relationship. So I cannot do that directly from mass because both of those ingredients have a different molar mass. It's a totally different relationship. So gotta go moles. So we're gonna look for moles of water given the mass of water. Again, we're going to use that conversion factor, our favorite. Our 1 mole equals molar mass. Moles are going to be on top. Molar mass of water is down below. Our molar mass of water is about 18.02, I think, something like that. Ugh, why can't I make a dot? Grams will cancel, and I should get about 4.717 moles here. You'll notice I've kept some extra significant digits here, and that's okay because I don't need to fix my digits until the end, so it's okay to keep some extras. What's not okay is to cut it off prematurely, so keep extras above prematurely cutting. All right, now that I've got moles of one thing, in this case water, I can use it to find moles of what I actually am interested in, which is in this case ammonia. So step 2 is my mole ratio from yesterday, so I'm going to look for moles of NH3 using moles of H2O. So this is my mole ratio step. So I'm looking at the relationship between water and ammonia. I'm looking for ammonia, so my 4NH3 will go on the top and my 6H2Os will go on the bottom. So 4.717 times 4 divided by 6, and we should be able to get 3.145 moles. Again, I'm just keeping some extra digits. All right, step number 3, home stretch. This time, now that I've got moles of NH3, let's put that in here, I can take those moles of NH3 and I can convert them back into a mass using that molar mass. So mass of NH3 is going to be my moles that I just calculated. And I'm using my molar mass relationship. In this case, I want to get rid of moles, so moles will go down here at the bottom. Molar mass will be needed on the top, and we've got about 0.31. And my final answer then should be about 54 grams. Dun 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 dun! All right. Oh, pesky arrows. Why do you do this to me? Your turn, folks. So you're going to try this one on for size. You're going to pause the video. Then you're going to play, and you're going to see if you got it right. No cheating. Set up the problem as usual. Pause now. All right. If you're on this slide, you better have tried it already. Stupid arrow. I'm going to fix that now. Here's our balanced equation. This time I have 0.50 grams, and I want to know how much chlorine I'm going to need to react with it. Same steps as always. I'm going to start with step 1. Where I have the number, I'm going to start with P. I've got grams of P. I need moles of P. Moles of phosphorus. I'm going to take my 0.50 grams using my mole and gram conversion factor. I want 1 moles on top. 1 moles. That's not plural. It's just 1 mole. And my molar mass for phosphorus down below. And I'll do some handy-dandy math. 161 moles. There we go. And now that I've got moles of one ingredient, I can use it to find moles of anything else that I want. And in this case, I want moles of chlorine. So step 2, I'm going to find moles of chlorine using moles of phosphorus. This is where I'm going to use that handy-dandy conversion factor out of coefficients. I want 3 Cl2s on top. And I want 2 P's on the bottom, so I can get rid of my P's. And that will leave me with 0.0242 moles of Cl2. And lastly, step 3, I'm going to convert those moles back into mass. So mass of Cl2 using my moles Using my conversion factor, in this case I want grams on top, moles on the bottom, and my molar mass of Cl2 is 70.906 since there are 2 Cl's. Final answer then should be 1.7 grams. Did you do it? Did you get it right? I hope you did. Let's practice. Yay! It's so much fun. All right, good luck. We'll talk tomorrow. Ciao.